Hello, and welcome to our presentation on using the GeoEvent Server SDK to develop custom components for GeoEvent Server. My name is Eric Ironside, and I'm a product engineer on the GeoEvent team. Presenting with me today is Brett Phillips, a software engineer also on the GeoEvent team. GeoEvent Server is a functional role bringing real-time GIS to the ArcGIS Enterprise. It provides 5 key capabilities when working with your real-time data. The first is ingesting high volume and high velocity data from connected devices, sensors, and the larger Internet of Things landscape. The second is to refine or enrich that data and to identify patterns of interest on the fly using real-time analytics. The third is to introduce a big data storage solution to support the volume of data being received, one that can be scaled and support configurable retention settings. The fourth is to extend the visualization capabilities of the ArcGIS Enterprise through stream layers for live feeds, as well as both dynamic aggregations and discrete feature display through enhanced map services. And finally, the fifth is to be able to disseminate information through notifications or actuation back to people and devices in the field and directly impact the environment in which those devices reside. This slide summarizes the main concepts behind GeoEvent Server. I'm going to give a high-level overview here, and we'll go into a bit more detail in certain areas later in the presentation. First off, we have adapters and transports which, when combined, define a connector. A connector represents a type of input or output that users can create to ingest or disseminate data. Inputs and outputs trade events with GeoEvent services which analyze and filter the data. Within a GeoEvent service, routes from inputs to processors, filters, choice elements, and finally back out to outputs define how data is analyzed and flows through the system. Data stores help us connect to folders, service directories, and portals for data access. Geofences allow us to do real-time spatial analytics on events as they flow through the system. And GeoEvent definitions and tags allow us to manage the event schemas flowing through our system. Finally, some people are surprised to learn that GeoEvent has a Swagger API. It is available and can be pretty useful, but that's a different presentation for another day. This is our agenda for today. The first thing we're going to talk about is creating and configuring connectors in GeoEvent Manager without customization. We'll also talk about utilizing existing custom components so we don't reinvent the wheel. Next, we will do a review of the GeoEvent SDK at a high level, going through all of the common items needed for developing custom components. Then we're going to walk through developing each of the types of custom components that are available through the SDK. Towards the end, we'll wrap it all up with some notes on building and managing your custom project, followed by a summary to review what we've covered today. The first thing we're going to talk about is configuring connectors, which can be done without any custom coding. Functionally, when a user selects an input or an output, they implicitly select the component inside GeoEvent Server that knows how to receive and send data. We call that component a transport. And the component that knows what the data looks like, which we call an adapter. The adapter can convert raw data to and from GeoEvents. A connector is the unique combination of one transport and one adapter. So here is an example of using an input and an output connector. The input is created based on a connector which specifies a TCP transport and a text adapter. Once the transport is started, it accepts raw bytes over TCP. The stream of bytes is passed to the adapter for parsing. The adapter parses the bytes and produces GeoEvents that are sent out to all of the different services. For the output, the reverse happens. The adapter accepts the outgoing events from the services. It deconstructs the GeoEvents into the outgoing format, in this case JSON, and the transport takes that data and sends it along. This occurs until the transports are stopped. As I said, a connector functionally provides the user the ability to create inputs and outputs. A connector's purpose is to hide the technical details the end users don't have to care about. Some of the properties may be hard-coded and hidden entirely. Other properties may be moved under the Advanced section and get default values that users may only rarely change. Finally, a connector can be used to provide contextually specific property labels. A connector can be very specific, or it can be very general, depending on the need. This slide illustrates how an input connector is created using available transports and adapters. For example, the received GeoJSON on REST is composed of an HTTP inbound transport and a GeoJSON inbound adapter. It is important to note that you can create new connectors that are not part of the core offering by combining the existing transports and adapters. You can do all of that in the GeoEvent Manager UI without writing any custom code. The slide also shows the inbound transports and adapters that are available both out of the box and on the Esri gallery. Similar to inputs, the output connector is made up of an outbound adapter and outbound transport. For example, the send an email output connector is composed of a message formatter adapter and an SMTP transport. There are a variety of outbound transports and adapters that are available out of the box and on the Esri gallery. With that, I'm going to show a demo on configuring a new connector in the GeoEvent server. So here we are in GeoEvent Manager. I'm on the Site tab on the top right and the GeoEvent tab, Connectors tab on the left-hand side. This list is all of the connectors that we have in GeoEvent Server that are out of the box. I can sort these, or I can filter these by both the inbound and the outbound types, so I can see which ones are inputs and which ones are outputs. And I can do a search here too. So if I type in watch here, I can find all of the connectors that would allow me to watch a folder for a file. And the first thing that I notice is that I can do CSV, GeoJSON, or JSON files, but I can't do XML files. So I'm going to create a new connector that will watch a folder for XML files. So as we come into here, we're going to take a name of watch folder for XML. I'm going to give it a label that is a little more descriptive, just so that users know what it's supposed to do, watching a folder for XML files. And then I'm going to set the type to be input. The adapter is an XML adapter because we're trying to parse XML. And then the transport is just going to be file, which is watching for files on the folder. And finally, the default input name, let's just go ahead and use the same name that we used at the top there for watch a folder. Now it's time to look at the properties. So all of these properties listed here are the properties that come with both the XML adapter and the file transport. And by default, they're all shown to the user and they have to choose something for them. But I want to make it a little bit easier on my users. So the first thing I want to do is, is this a text file? Yeah, it's an XML text file. The batch flush interval is something they wouldn't have to see, and then the channel ID is also something. So I'm going to set these as hidden, and I'm going to hard code them so that the user will never have to change them or see them. So the batch code is fine, just be using the default, and same thing with the channel ID. Okay, so that hides those three. It sets them. They'll always be set. We don't have to worry about those again. And then some of these other ones here, I also want to move into the advanced tab because I don't want to bother the user too much here with having to set a bunch of stuff. So all of these deal with GeoEvent definitions, as well as the date formats and the geometry from fields and all that kind of stuff. So I'm going to move that over to the advanced. Hopefully they won't have to change those every single time. And then I'm also going to move these two for number of lines over there as well for lines per batch and lines to skip, since they won't be using those that often either. So now I'm left with just this small batch of properties that the user is going to have to set in order to make these work. I'm actually going to move some of these around. So the input folder data store is going to go up to the top. So that's basically what folder do I want to start searching for in. The XML object name I can move down to there and include subfolders. Sure, let's go ahead and move that up to there. So, we got the folder that you're looking in, the subfolder that you can, that you're going to be looking for files in. Do you want to include subfolders, yes or no? And then a file filter, so star.xml maybe. Let's go ahead and set that as the default. And delete files after processing is fine, and input file filter. So we've got all that set up, and I'm going to go ahead and save this, and that will create our watch a folder for XML connector. So now back on my connectors page, if I search for watch, you'll now see that I have this watch a folder for XML files. It's an inbound connector, and if you press the pencil over here, we can come back in and change any of these properties. So I'm just going to cancel on that since I don't want to change anything at the moment. And now it's time to use it. So if we run back to services and on the inputs, I'm using a 10.8 version of GeoEvent here. If we add an input and we type in watch to filter here, you can see at the bottom here we've got our watch a folder for XML files. So when I select that, we get creating a new input. It's watch a folder for XML files. The default name is watch folder for XML. That's just what we set it at. And then we've got the input data store, the subfolder that we want to look at. Do we want to include subfolders in there? The name of the XML object we're trying to parse out, delete files after processing. That's great. And if we hit the Advanced tab, we can see here's all of the things that we hid or moved over to the Advanced tab because we didn't really want to deal with them every time. Notice that the hidden properties are not even shown, so we can't even change the, is an XML a binary or a text file. And so that's how you would change or create a new connector in GeoEvent Server based on the out-of-the-box adapters and transports. For our second topic, we're going to talk about not reinventing the wheel. A lot of work has been done over the years to develop a large number of custom components for GeoEvent Server. Most of them have been shared in some capacity, so we're going to talk about finding and deploying those custom components. I've mentioned the GeoEvent Server gallery a few times so far. This gallery offers a set of adapters, transports, and processors that are not part of the out-of-the-box installation, but can be added to your GeoEvent if you need them. There are actually several galleries, one for Esri managed items, one for partner items, and one for users who post their own. Typically, each gallery item has a zip file associated with it that you can download. This archive should contain everything you need to get started. Another source of existing custom components is GitHub. There are two places a custom GeoEvent item may be hosted publicly. The /Esri contains a set of repositories that are publicly shared. Anyone can download, fork, and/or compile the source code on their own. There are also a number of user-hosted projects out there that can be utilized. A final source of existing components is Esri Professional Services. You might consider contacting your account manager to see if they have already developed the component that you're looking for. If you get lucky, they may already have it in their library, and cost may be minimal to have them install it for you. Historically, GitHub repositories have contained the source code but not provided any compiled binary files that can be directly deployed to GeoEvent. One frequent job of maintaining one of these repositories is actually fielding questions of building the deployable files for people. For this reason, we recommend that each repository should have a release, which is a GitHub option that shows up on the repository towards the bottom right. A release should contain a compiled jar and project documentation in a downloadable zip format. If you own or manage a repository on GitHub, you should strive to do the same so others can access what you have built. If you have access to a repository but a release is not provided, it is possible to build it yourself. Here I'm going to show you the process on Windows. Running as an administrator in a command line window in a temporary directory, you will need two items installed on your system. The first is Java 1.8 or later. The second is Maven 3.63 or later. Just grab the latest version, they'll all work. Use Git to clone the repo to your local temp drive. Then cd into that new the new folder that's created when you downloaded the repository and run maven run clean install. Maven will create your jar file for you, and the resulting jar file will be in the target directory of the projects folder. Once you have compiled the jar, you have to upload that file into GeoEvent Server. You can do this in one of two ways. The first is you can copy the jar file directly into GeoEvent's deploy directory, which is found under GeoEvent's installation directory as shown here for Linux and Windows. Or you can upload the file using GeoEvent Manager's Add Local buttons. These can be found on the Site tab under the Components menu item. In order to remove a custom item from GeoEvent, you must delete the jar file from the deploy directory while GeoEvent is running. If you don't delete the jar file while GeoEvent is running, it will be replaced by the configuration on the next time that the service is started up. So please make sure that you delete to remove things while GeoEvent is running. There is no GeoEvent Manager method for removing custom components. Which brings us to our next demo. Here I'm going to demonstrate deploying custom components from the GeoEvent gallery. So if we start out at GeoEvent Manager, this is 10.8 once again. So in this case I've got a GeoEvent service that's all set up, my input and my output. And if I sample this route, then I can see that the events that I'm getting in here, they actually have this string field with a bunch of values that are separated by commas. And what I want to do is I want to split this string field out into a bunch of different events. Each event has a value in this string array. I know that GeoEvent can't do that by itself, so it's going to need some help, and I'm going to go to the GeoEvent gallery and see if I can find something there that will help. So this is the gallery. You can see we've got 11 processors, 23 connectors, a bunch of tutorials, so there's a lot of good information on this page. I'm going to search at the top here for something that will split fields or splitter fields, and lo and behold, I find a field splitter here. So if we open that field splitter up and read some of the instructions here. So field splitter processor, it's going to split comma separated values of a string field into separated GeoEvents. That's exactly what we need. So this field splitter processor is what I want to grab. So if I scroll on down here and I find the latest release, which is compatible with any version 10.4 or greater, I'm going to download that. And when I get that opened and unzipped, I'll find that I have this folder here. So there's two documents in here. One's a release history and the other one's the user guide. So the release history, if you open that up, it's going to always tell you how many releases there have been, when they were released, and the issues that we fixed or the enhancements that we added for each release. And the user guide here is going to give you information on deploying this, when to upgrade, what to do during an upgrade. It's also got some instructions on how to use the field splitter, and discusses what it does. And so reading through this, this is exactly what I need. And so I'm going to go into the components directory here, and these jar files are really what you end up deploying. So these are the custom components that you can deploy into GeoEvent Server. And the field splitter processor is the one that I want to do here. So I'm going to switch back to GeoEvent Server, and I'm going to go to the Site tab at the top right. And I'm going to go to the Components tab on the top left, and we'll select processors from the menu item here. And just to show you that we don't have anything like this in here, we're going to type split here, and we don't have anything. So I'm going to add a local processor, choose files, and I'm going to navigate down into that folder that I just unzipped, and I'm going to choose the field splitter processor. And when I add that, I'm going to give this just a second to load up, and then we're going to type in split one more time, and there it is. So we've got a field splitter processor in our GeoEvent, and it's version 10.4.0. Like I said, this is 10.8.0, so we're all good there. It seems to be running, so it's all good. And that version does not have to match what the GeoEvent server is. And if we run back to services, and open up our service, we get rid of that route, and we'll drag on a new processor. The field splitter should be in our list, and there it is. So now we have a field splitter. And the value, or the name of the field that we want to split is called values, and we want to split on commas. And so throw that in there, connect, publish, and sample, compare. And event comes through. Now notice we've got one event on the left with our comma separated array, and on the right we've got 6 events, which is good. So that did exactly what we needed it to do. So we got 24, 14, 10, 32, 8, and 11. So that's all of our numbers. Notice they're not in the same order, or that the array is, so you can't count on the order that they're coming out as, but it definitely split them up into separate events. So that's how you would deploy a custom component on GeoEvent Server using the GeoEvent Server Manager. If you wanted to do this without GeoEvent Server Manager, that is possible. I'm going to drag a processor on here, and you'll notice that I do not have a multi-cardinal field splitter in here anywhere. And that was one of the other processors that we had available to us in the download here. So this time what I'm going to do is, instead of going through the user interface, I'm going to actually go grab this file here. I'm going to copy this, and I'm going to put it into the deploy folder. Now the deploy folder is a special folder that GeoEvent uses. It's down in the GeoEvent install. So we're at Program Files, ArcGIS Server, GeoEvent. I took the standard install for GeoEvent. And the SDK folder is down here. We're going to talk about that in a little bit later in the presentation here. But the deploy folder is really what I want to get to. So here's that field splitter that we just uploaded. So notice that the user interface stashes that jar file into this deploy folder. And so we don't have to go through the user interface to get jar files in here. So I can just paste my multi-cardinal field splitter in here. And now that it's there, what will happen is GeoEvent will grab that new file and make it available to us here in GeoEvent Manager. So now if I grab, or if I pull in a processor and I pull this down, you'll notice we now have a multi-cardinal field splitter. And okay, so I'm going to publish that. Everything's good. So that's the two ways that you can deploy custom items to GeoEvent. So the first was through the GeoEvent Manager user interface under the Site tab to pull in new components for transports, adapters, and processors. And then the second one was going through the deploy folder on the disk in the install directory. So the last thing I want to show here is how to delete a custom component. So if we've got this multi-cardinal field splitter in here and we wanted to either update it or delete it altogether, what I recommend is that you go ahead and remove the custom component first before you upgrade. So the way you delete something is you actually go into that deploy directory. So we're back here at Program Files, ArcGIS Server, GeoEvent Deploy, and you find the jar file that's there and you delete it. Now, one important thing that you need to be sure of is that you're deleting it while GeoEvent is running. If GeoEvent is not running, then it will just copy a copy of that jar file that it has in a cache of its configuration back into this deploy folder. So you definitely want to make sure that GeoEvent is running so that it can discover that that jar has been deleted. Once that's deleted, back here in our service, it already knows we've got an error. All right, we don't know what that is. But if I do this here, then I can tell the multi-cardinal field splitter is not available. So that proves to me that it's been deleted from the system. So if I publish that and we start it up again, then everything's happy and fine. And with that, we're going to go back to our presentation and move on to talking about the SDK.
Thanks, Eric. Up to this point, we have gone over creating connectors and processors using the GeoEvent Manager as well as the Esri Gallery. But what happens if you need something that cannot be created using these out-of-the-box components or even the available repositories? Well, that's where the GeoEvent SDK comes into play. Using the SDK, you can customize various parts of GeoEvent. These parts are currently shown in yellow. You can create your own transports, adapters, connectors, and processors. And within the context of each one of those components, you also have the ability to manipulate data stores and geofences, as well as create or update GeoEvent definitions and tags. The GeoEvent SDK is installed along with GeoEvent Server at the following locations depending on your operating system, whether that be Linux or Windows. Within the SDK folder, you will find various resources that will help you get started. The API folder contains the Java doc for the SDK. The repository folder contains a set of libraries that you can use to compile against when writing your own custom code. The samples folder contains example code for the various components from connectors all the way to processors. And then lastly, there's a developer guide, which is an in-depth document describing the software architecture, how to work with the different components, and a synopsis of each sample project. Before you go ahead and write any code, I strongly suggest you go ahead and read the developer guide, as it will help you along the way. GeoEvent is built on OSGI, which is a Java framework for developing and deploying modular software. This framework allows you to divide your code into bundles that get managed individually by the underlying system. It takes care of everything from dependency injection all the way to lifecycle management. Now, there are 4 important files needed when creating your own custom components. First, a blueprint configuration file, which tells the underlying framework how to create your component. Then, a service class, which is ultimately a factory for creating new instances of your component. A definition class, which helps define the metadata and properties that are required. And then an implementation class, which includes all of your component's application logic. We are now going to go ahead and take a look at the code for each one of these files. The configuration file is based on Blueprint. The bean is a pointer to the Java class that implements the service, in this case the adapter service, and it also includes any dependencies that the class relies on. The bundle context is one of these dependencies that is required as it is needed in order to interact with the OSGI framework, but other dependencies, such as the data folder, are optional. In this example, we are also using a reference. This allows us to access other SDK items such as the messaging interface. Lastly, we have the service, which exports the bean with the given interface to the service registry. The responsibility of the service class is to create new instances of your component. It does this by instantiating the definition and passing a reference of that definition to create an instance of the implementation class. In this example, you can see that I also have included the optional data folder property that was in the prior configuration file. With that being said, it's important to note that this is an optional property and your service classes may not require any properties other than the definition. The definition class is responsible for defining the metadata and properties needed for your component. The definition can be written in either a Java class or XML file. Here you will see that we have defined the label and description of our component in a Java class, and we have also localized the strings. It's also important to note that when you define your domain, you should avoid com.esri.ges. This is because this domain is reserved for out-of-the-box components. Now, when we look at the property definition, you can see that we can specify attributes such as name, type, default value, a list of allowed values, localized versions of its label and description, as well as other properties that may be dependent on, in this case, compress output. Once the property definitions have been created, you must add them to the property definitions list. And like I said in a previous slide, property definitions can also be written in XML and will include the same exact capabilities as if you were to write it in a Java class. At the end of the day, it's really just a matter of what you prefer as a developer and what you are more comfortable writing. The implementation class is where all of your application logic exists. There are 3 lifecycle stages that are common amongst all implementation classes: the creation stage, the initialization stage, and the validation stage. In the creation stage, you will need to extend the base class, as this will provide you with access to out-of-the-box functionality. Now, when this class is instantiated by your service class, it will receive the definition and pass it to the base class constructor. Once the instance of your class has been created, you will enter the initialization stage. Here, you will use the afterPropertySet method in order to initialize the object's properties. You can use the getProperty method from the API in order to get any user-defined values. In this case, we are getting the event size value, casting it to an integer, and assigning it to the event size instance variable. Now, after your properties have been set, you will enter the validation stage. In the validation stage, you can go ahead and validate any properties to ensure they are what you expect them to be, whether that be you expect them to have a certain data type or be a certain value. Now, when you develop your components, I strongly urge you to use the bundle logger in order to log any helpful information to the user. After retrieving the logger, you can then make use of methods such as trace to log events. You can pass many arguments to these methods and reference them within your string using index notation. It's important to note that each log method is also overloaded, allowing you to pass in the exception in order to add the stack trace to the end of the log message. You also have the capability to pass in localized strings if that is desired. You should now be familiar with the common implementation pattern of creating components. Now we're going to review each component further, discussing how each implementation class differs. First, we're going to talk about transports. Transports control how data moves in and out of GeoEvent. Before looking into the code, it is important to understand the life cycle of a transport. It first begins in a stopped state and will stay in this state until the user decides to turn on the connector. Remember that a connector is simply the combination of a transport and an adapter. So for an inbound connector, we pair an inbound transport with an inbound adapter, and for an outbound connector, we pair an outbound adapter with an outbound transport. Upon starting the connector, the server will call the start method, which will send the transport into the starting state. Here, the transport will read and validate its properties, and once complete, enters the started state. It will then remain in this state, consuming and emitting data until the user decides to turn off the connector. By turning off the connector, this will cause the server to call the stop method, closing its resources and reallocating memory. Now, sometimes this process does not run smoothly and errors can occur. In this case, the transport will enter an error state. Here, you will be able to catch and handle the error as desired. Looking at the lifecycle from a code standpoint, in the start stage, you will see that we override the start method. This is where you will handle the starting of the connector once the user requests to turn it on. We set the running state to starting, instantiate a new thread, and start that thread. This will kick off the run method and allow us to begin moving data in and out of GeoEvent. The top picture shows how an inbound transport handles incoming data. In this scenario, the thread's run method will get data, add it to a byte buffer, and send the data along to the inbound adapter's byte listener. The bottom picture shows an outbound transport's receive method. This is where the transport will receive the data from the outbound adapter to then be sent out or emitted to the connected devices. Now, once the user decides to stop the connector, the stop method will get called. The super method will send the transport into the stopping state and as a result, stop the flow of data. We have gone through the steps required to bring data in and send data out of GeoEvent. Now, we need to be able to transform that data to and from GeoEvent objects in order to complete the creation of our connector. We do this by creating an adapter. With other components in GeoEvent, such as transports and processors, we follow a specific lifecycle. However, the adapter does not have its own lifecycle, but instead it is event-driven. For inbound adapters, it is important to understand the base class that you will be extending. Because it is an abstract class, you will need to implement the adapt method. In this method, you will need to handle the transformation of your data into a GeoEvent object. Earlier, we saw how the transport sends data to the adapter via its byte listener's receive method, hence why the adapter is an event-driven component. Once the inbound adapter receives that data, it will call the adapt method that you have overridden. After the data conversion takes place, it will send the GeoEvent object to either a processor or an outbound adapter. If you need to handle your own logic upon receiving the data, then you can do so by overriding the receive method. If you decide to go this route, then please keep in mind that you will need to call the GeoEvent listener's receive method, otherwise you will lose your data. Similar to an inbound adapter, the outbound adapter will receive GeoEvent objects through its receive method. You will need to override this method in order to transform the received GeoEvent objects back into the data type required for your connected devices. Once you have successfully converted the data, you will need to send it to the outbound transport by calling the byte listener's receive method. Up to this point, data is flowing from connected devices into GeoEvent and adapted into GeoEvent objects. Now, you can develop your own custom processors to perform specific actions on the event data. Just like transports, processors have a specific lifecycle. The lifecycle starts once the user has published and started their GeoEvent service. This kicks off the creation stage where the component is retrieved from the service registry and an instance is created. After this occurs, we enter the initialization stage where the processor's properties are set. Once set, the properties are validated to ensure their accuracy before entering the processing stage. It will stay in this processing stage, processing events performing specific actions such as enrichment or identification until the user decides to stop the GeoEvent service. Once stopped, the processor will enter the shutdown stage where it will free up resources and reallocate memory. The most important method within the lifecycle of a processor is the process method. This is where you will retrieve and augment the event data. In this example, we are augmenting the incoming GeoEvent by retrieving its definition in order to populate the incoming event with an extent. With processors, there are also some optional methods that could help with resource management. First, the shutdown method, which gets called when GeoEvent Server is shutting down. Now please keep in mind that I did say server and not the service. The onService start method will get called when the GeoEvent service is starting. This is a good place to perform some initial logic needed for your processors. On the other hand, the onService stop method gets called when the service is stopping. This is where you will want to clean up the processor's resources. Lastly, it is important to note that GeoEvent objects are not copied due to performance reasons. Rather, they are passed as read-only. If you plan to mutate GeoEvent objects, then you should override this method isGeoEventMutator and return true. When developing your components, you may run into problems where you will need to debug your code. To successfully configure debugging, you will need to navigate to the etc folder and find the following configuration file. Open it up as an admin, uncomment the lines seen in the picture, and continue the numbering scheme. Here, we have added 15 and 16, but this will depend on the GeoEvent build that you are running. In the configuration file, you will also see what port our debug session is set to listen on. I am currently using IntelliJ for my development, so your process may slightly differ. However, in your IDE, you will want to configure debugging for a remote Java application. Enter the host that GeoEvent Server is running on, and enter the port number. You will also need to specify the Java version. For releases 10.8.1 or earlier, you will want to specify JDK 5.2.8, whereas for releases 10.9 or later, you will want to specify JDK 9 or later. Now, I'm going to go ahead and run through a debugging demo where we will debug the field splitter processor. I have a service here which contains an input, a processor, and an output. To ensure data is flowing correctly, I will go ahead and sample my two routes. Let's open up the sampler. We will change the sample size to 1, enable the sampler, and select the route going into the field splitter. We can see here that we have received data. Now let's see what's coming out of the field splitter. We are yet to receive data, so we can assume that something went wrong. Let's dive deeper into the problem and set up our environment for debugging. In order to do this, we need to navigate to the etc folder and open up the GeoEvent configuration file. Let's go ahead and search debugging, and we will see that we have to uncomment these lines to enable remote debugging. If you remember correctly, we also have to continue the numbering scheme. Here we have 30, so we're going to add 31 and 32. Now in our IDE, let's add our configuration. We are going to choose remote. We will go ahead and name it demo. For our host, we want to put the host that is currently running GeoEvent. Make sure our port is 5005, and then in my case, JDK 9 or later. Let's hit apply and OK. Now, we will hit the debugger to turn it on, and we can see that we have connected to the target VM. Now let's go to the process method, and inside the process method, we can see we are creating a new instance of the GeoEvent splitter. Let's go ahead to that class. In that class, we can see that we are implementing runnable, and then we see the run method. This is where the magic is happening. Let's go ahead and set a breakpoint on line 251. And then let's start stepping through the code. Up to this point, everything seems fine. We have a field, and it's got the data. Now let's go ahead and get the field value to split. So we have the field values that are delimited by commas. And now we can see, let's go ahead and split, but we see, oh, the field splitter is null. So something must have gone wrong at some point throughout the process. So let's go up to see where we actually initialize this value. We will go ahead and release the debugger, go to the top. Okay, so we see that we do have field splitter, but it looks like it's never assigned. So we can go to the after property set method, and in here we see that we are assigning the field to split variable, but we don't see field splitter here. So let's go ahead and add field splitter. We'll go ahead and use the get property method, passing in the string name, which is field splitter. And then we will get that value as a string. Let's go ahead and save that. And now we will need to rebuild our processor. So we will go into the terminal and type in Maven clean install. Once this is done, we will have a target folder, and in that target folder we will see our new jar. I have replaced the jar file within my deployed directory, and now I can test my processor. At first glance, I can see that I do have data coming in and out of my service. Let's open up the sampler and test to see the data going in and out of the field splitter. Let's change the sample size to 1 and enable the sampler. Let's also select the route going into the field splitter first. We can see that we do have data. Now let's see what's coming out of the field splitter. We also receive data coming out of the field splitter, and we can see that we only receive a single value for field 3. Let's go ahead and change the sample size to 10 and resample the data. We'll sample the data going into the field splitter, and we will compare it to the data coming out of the field splitter. Once we've received all of our data, we can confirm that this field splitter is working correctly. So if we scroll to the top here, the first record that came in has the value for field 3 as 24, 32, 14, 10, 11, and 8. If we scroll to the top here, we could see field 3 has 32, 24, 14, 11, 8, and so on and so forth. This helps us confirm that our field splitter has been fixed and is working correctly. Now let's go back to our presentation.
Now we'll talk about how to build your project. We've heard from various sources that one of the more daunting tasks of developing a new custom component is using Maven to build a bundle. I hope this section will expose some of the wizardry behind Maven and provide some insight into how it works when building custom components for GeoEvent SDK. When you create your new custom component project, be sure to create it as a Maven project or import it as one. I suggest you start with a copy of one of the sample projects at a minimum. At the top level of your project, there will be a Maven pom.xml file that will determine how the project is built and packaged into an OSGI bundle. For processors, there is generally one pom.xml file for the project, but connectors generally have a parent-child set of pom.xmls, one for the parent and one each for the child adapter and transport. Inside a specific components project, you will have a Java source code folder and a resource source folder that provides an OSGI configuration file, your string files, and potentially some definition XML files. Taking a look inside of a pom.xml file, the first part of the pom is the group ID, artifact ID, and the bundle name. The group ID is the domain of the component, so I suggest you use one of the three shown here for adapter, transport, or processor. Note that com.esri.ges is reserved and should not be used. Next is the artifact ID. This will end up being your component's identifier. I like to use Java package convention, naming convention for the artifact ID so that the combination of the group ID and the artifact ID matches my source code's package name. You should also note that the combination of the group ID and the artifact ID defines the path to your internationalization string files in the resources folder. Then we have the name of the bundle. Here I use a token to reference the artifact ID and append either a -processor, -adapter, or -transport. An example of how all this fits together is shown here. The text is color-coded so you can see how it all fits together. The group ID is com Esri GeoEvent processor, and the artifact ID is add_xyz. The path where the bundle will look for its internationalization strings is going to be in the project's resources folder under the folder structure com Esri GeoEvent processor add_xyz.properties. And the suggested Java package would be com.esri.geoevent.processor.add_xyz. The next part of the POM file is the version, metadata, and properties dependencies. I set the version to the revision, which is managed in the properties below. Next is the metadata for the bundle, including a description, URL, and organization information, where the organization URL here actually points to the help documentation if available for this component. If not, don't worry about it. Packaging is set to bundle. For properties, the revision is set to be the target GeoEvent Server SDK you want to compile against. This doesn't have to match your current GeoEvent Server's version, so I suggest using either 10.4 or 10.6 if possible. I add a project.release property here so I can manage my release number separate from the GeoEvent SDK revision. Next are the property file encodings, and then the versions of all the plugins and dependencies. I usually put the encodings and the versions here in the properties where they are easy to see and maintain. And finally, there's the dependencies. This section tells OSGI what other bundles your bundle depends on. You will always have the GeoEvent SDK dependency, and note that it points to the GeoEvent SDK version equal to the revision property. The third part of the POM file tells Maven how to build your component's OSGI bundle. The first part here is for resource filtering. This directs Maven to crawl the resources directory and replace any $curly brace tokens with the values from the pom.xml file. Next is the Maven compiler plugin. It compiles your code against the chosen GeoEvent SDK. Note that with GeoEvent 10.9 coming out, we'll be switching to Java 11, so you can compile your code against Java 11 by replacing the source target 1.8 with release 11. Compiling against 1.8 makes your code forward and backward compatible, but Java 11 will be more optimized and perform better on a 10.9 system. So if you don't need to be backward compatible beyond 10.9, then use Java 11. Otherwise, stick with Java 1.8. Finally, there's the Maven bundle plugin that takes the compiled files and wraps them up into the jar file for deployment. There are some important build instructions that you can supply. I'll get to those next. What you see here is probably the minimum set of instructions that can be used in most situations. So what instructions can we set? The first is the name of the output jar file. We'll set this to include the project's name and the revision number. Next is the ArcGIS domain. As you might suspect, this is a custom instruction that is used by the GeoEvent SDK to set the domain on your component. If you don't set the domain on your component, it won't load into GeoEvent properly, and the easiest way to set it is to do it here. The bundle contact information is also easiest to set here since I put the contact email property up into the POM properties above this. Optionally, you can add an export package instruction to restrict what other bundles can see or use from your bundle. You can modify the default import package instructions if you need to make certain libraries optional or omitted, and you can even embed dependencies into your jar file, but this isn't usually recommended unless absolutely necessary. That covers the nuts and bolts of a standalone pom.xml file that could represent a single processor, transport, or adapter. But what happens when you are creating a connector with both transport and an adapter? For that, you'll need to create a hierarchical project structure with a parent at the top and modules for the transport and the adapter. The parent pom.xml file defines as much as possible, and the module or children pom.xml files subfolders build on what the parent has defined. So for the parent POM, we're going to try to abstract as much information from the child modules as we can to store everything for the project in one place. Here we see a lot of the same information we saw from the single POM that we just discussed. But note that the parent is using a different group ID of com Esri GeoEvent parent. We then define the modules inside of the modules tag. These values should match the underlying folder for each module. I reuse the artifact ID of the parent with a dash adapter or dash transport for module names. In the name, I added the dash parent moniker. The packaging directive is set to POM to indicate that this is a parent POM that is to be used by other POM files. We've got the common properties that will apply to all submodules. It is very important that you declare the versions for all of your dependencies in the parent POM. Once again, I store them here in the properties to make them easier to find and use, and they should be in your parent POM. On to the dependencies. It is recommended that you put all of your dependencies for all modules into your parent POM. This centralizes everything and ensures your dependency tree is consistent. Also notice that I'm setting the version here in the parent for all of these dependencies. If you don't do it this way, you run the risk of getting dependency cycles and/or version mismatches. Also notice that I've wrapped these dependencies in the parent POM with a dependency management tag. This tells Maven the underlying modules have the option of using these dependencies, but don't have to if the module doesn't need them. Next, we define the plugins within the build. Nothing changes here from our single POM configuration, but notice that, like dependencies, we've wrapped the plugins in a plugin management tag. Once again, this gives the underlying modules the flexibility to use the plugins if needed, or ignore them if they don't need them. Moving on, so for the child module's POM, we first need to tell it where its parent is. So when we start this POM, the very first thing we're going to put into the POM is the parent tag. This gives the module the group, artifact, and version of its parent. Use the revision token to inherit the version from the parent. This way we don't have to modify the version of all of our POM files if we decide to change. We just modify it in the parent revision property. Next, the group ID is set to be the path to either adapter or transport. The artifact ID is set to be the same as the parent artifact ID along with either dash adapter or dash transport. Name will use the artifact ID. We'll add a description here for a module that includes the project release token. And packaging is set to bundle, so Maven produces a jar file. For dependencies, only add the dependencies that are required by the module. When we add dependencies for a module, only use the group ID and the artifact ID to define it. This will cause it to inherit the version set in the parent POM and help avoid dependency cycles or mismatched dependency versions. The build instructions for the module will be similar to the dependencies. When adding the plugins for a module, only use the group ID and the artifact ID to define it. This will cause it to inherit the version and other properties set in the parent POM. For the Maven bundle plugin, you can override the configuration and build instructions if you need to do more or customized items with the module. If your module has specific needs like embedding a dependency, this is what that would look like when you override the configuration instructions. Now we're going to talk about version compatibility and release management. There is a misconception that a custom component has to be compiled for a specific version of GeoEvent Server. This is not only untrue, it is harmful in terms of upgrades. To get a better understanding of this, I'm going to talk about how GeoEvent manages versions of components. All components are registered utilizing a URI that is built up by a domain, a symbolic name, and a version. From our discussion of pom.xml files, you might recognize these as the group ID, the artifact ID, and the revision. All three of these strings are required to create a URI for a component. If you are missing one of them or if it's empty, the component will fail to register and cannot be used within GeoEvent Server. For component URIs that are out of the box, the version is managed by GeoEvent Server. So if a configuration from 10.6 is imported into a 10.8 GeoEvent, the out-of-the-box components will automatically have their URI version updated from 10.6 to 10.8. This is not true for custom components. GeoEvent will not make any assumptions about the version of custom components. So in the upgrade scenario above, if you recompile and deploy the custom components using the 10.8 SDK version, their URI will no longer match what is in your 10.6 configuration. And when you import the 10.6 configuration into the 10.8 machine, all items based on your custom components will fail to load. It is for this reason that it is best to compile your custom components against the earliest version of GeoEvent SDK you ever expect to deploy against. If you do this, you will not have to modify your existing configuration as you upgrade GeoEvent over the years. Compared to GeoEvent Server itself, the SDK does rarely change between releases. At 10.8.1, there was an exception to this rule. GeoEvent made some changes to policy and disabled support for older versions of libraries, especially those related to XML and JSON parsing. Because of this, we've seen some situations where a new compiled version of the custom component is required for 10.8.1. So just to reiterate, your custom component version does not have to match the GeoEvent Server version that you're running. You should strive to compile against the earliest version that supports your custom capabilities. So if the version of your custom component is not changing over time, how do you account for the changes to your code as you fix issues and add enhancements? I add a property to my main pom.xml file called a project.release. Every time I make a new release of the custom component, I increment this number. Once I've done this, I can use the token in both the pom.xml and the strings files to indicate the release number. Specifically, I put the project.release tag into the description for both the bundle and the component, and this is important because it will display the description of the component within the GeoEvent Manager.
Throughout this presentation, we have gone over everything you need to know in order to customize GeoEvent using the SDK. We have learned that connectors are the recipe for creating inputs and outputs and consist of a transport to move the data in and out of GeoEvent and an adapter to convert that data to and from GeoEvent objects. We have also gone over processors, which allow you to perform actions on event data in real time. Here are a list of resources to help you get started. There are a number of examples provided with the SDK showing sample transports, adapters, and processors. In addition, you can find some examples on GitHub. We encourage you to listen to the various other GeoEvent and Velocity sessions, as it will provide you with further information about how to leverage our real-time products. That concludes our presentation. If you have any questions or comments, please submit them via the following link. Thank you for your time, and we hope that you have learned some valuable information about creating connectors and processors using the GeoEvent SDK.